All right. So welcome everyone. So today is the second session for this workshop. Just a minute. Yeah. Okay. Uh, Today's topic is single solution metaheuristic. Yesterday we have talked about the basics, fundamental ideas of metaheuristics. I'll go back and I'll show you what we covered. We covered what is search space, what is objective space. Then we moved on to see some ideas of exact methods and approximate methods, the classification. And then we saw some greedy algorithms, and we talked about neighborhood fitness landscape analysis. We did not cover local search. So we'll cover these things today. Before I proceed, I would like to revisit some of the concepts of neighborhood generation and fitness landscape analysis. And then we'll move on to today's lecture, which will start from local search. Okay. So let me just go to that slide. So this is the slide. So we first talked about representation, that a representation is very important, and this governs the efficiency and effectiveness of your meta heuristics. We can have different kinds of representation. We saw for a specific problem, you can have various kinds of representation. So you have to choose from the various you can actually work with. So we saw binary representation, real valued representation, discrete value representation, and permutation representation. We saw some examples of each, and then we saw what are some key characteristics of a good representation. It should have completeness. So from one encoding, you should have a path to move to the next encoding. Completeness is actually every possible solution can be represented by your representation. Connexity is says that from one solution you should have a path to move to the other solution. Efficiencies, it should be easy to manipulate. All right. Then we saw an example of 8 queen problem and how it helps to reduce the search space drastically if you represent the problem using permutation representation instead of discrete value representation. And then we saw mapping. So in some representation, you may not encode all the information, and you can keep um, uh, minimal features in your representation, and then you can use a decoder to obtain the exact solution for the problem. One example is scheduling problem. You can have the permutation of the jobs, but the exact value of the start times and completion time of the jobs can be obtained using a decoder. All right. And yeah, so we saw that, and then we saw an example of random key encoding. Then objective function. So the idea is you have a objective function for your problem, but it is not necessary to use the same objective function for your meta heuristics. You can use a different objective function. You can modify the objective function so that it guides your solution to a better local optima. All right. So that was the idea. We saw an example using exam scheduling problem where the original objective for the problem is a not good candidate to solve the problem, and we modified the objective such that it better guides the search towards local optima. Okay. Then we saw handling techniques, rejection strategy. We can reject a solution. Penalizing strategy. We will just move the penalty in the constraint to the objective function. Infeasibility in the constraint to the objective function. Repair strategy, where if we have an infeasible solution, we try to repair it to make it feasible. Decoding strategy. Inside the decoder, you add some features that it takes care of your constraints. This is what a decoding strategy is. And preserving strategy, it uses the representation. It chooses a representation in such a way that most of the constraints or some of the constraints are encoded using the representation. So the representation takes care of the constraints. All right. Yeah, so we moved on to S meta heuristics, and we saw the higher level idea of a S meta heuristic. We have a solution, we generate a set of solutions, and we move to the next solution. This solution which we are working with is known as the current solution, and then we obtain a candidate solution. How do we obtain a candidate solution? Using the idea of neighborhoods. So from each representation, we try to manipulate it slightly such that we get a new neighbor, a new solution to that from that solution. So this small modification is known as a move in metaheuristic community. And you should have strong locality in your move operators. What does a strong locality means? A small change in your representation should reflect a small change in the solution. This is what a strong locality means. All right. Then we saw some examples of move operators: two opt move, three opt move, insertion operator, exchange operator, inversion operator. These are for permutation representation. Bit flips and swap mutations, these are for binary. And we saw few examples of how we can generate a new neighbor, different kinds of move for different kinds of representation, and how those generates new neighbors. All right. Then we talked about how will we imagine a search space to be. So we can imagine a search space as a graph which has nodes and edges. The nodes are actually the solutions, and the edges represents the moves from one solution to the other. So a edge between S1 and S2 represents that you can move from S1 to S2 with one move if it is directly connected. If it is indirectly connected, say S2 is connected to S3. So from S1 to S3, you can go to from S1 to S3 using two moves. So here comes the idea of distance between one solution to the other. So we first imagined it as a graph, and then we defined distances in this graph. All right. Now, I hastily covered fitness landscape analysis. So I'll try to cover this again because this is very important. Since we are thinking a solution as a graph, a solution space as a graph, search space as a graph, the moves define how your landscape will be. What is a landscape? So if you come back here, you can think it as a geographical metaphor. So you have the solution space in the ground, and the objective function takes the altitude. So you can have a curve. That curve represents the objective function in these two dimensions search space, right? So if you have such a move, so from one, I'll come over here, right? So suppose for this solution, your neighbors are in this region. So suppose this is a swap move in a permutation combination, swap move. And your objective function becomes something like this. And how will this be in the graph? You have a solution S, and you can go to S1, S2, S3, S4, and S5. So suppose in this region, you have these five solutions, S1, S2, S3, S4, S5. Now, if you use some other move operator, suppose you're using two opt, maybe these solutions you will not be able to reach it using one move operator. In such cases, from S, you will go to suppose S6, S7, S8, S9, and S10. So these, when you represent it as the landscape for S, you create its neighbor, and what you will observe is this curve is not the same as the other curve. It may be like this. So your landscape changes depending upon the representation and the move operator you are using. Your neighborhood structure changes, and that changes the landscape you are seeing. It can give you a rough landscape. It can give you a very good basin-like landscape where all the optimas are coming together and you have just a big basin, and your global optima is at the end. If you don't get such a landscape, suppose you have a rugged landscape, your move operator and representations are such that you get a rugged landscape. In such cases, it is difficult. The metaheuristic can get stuck in local optima. All right. This is the global optima, but since it is rugged, you're not able to come out of the local optima, and therefore you are stuck at the local optima. So the move operators becomes very important in such cases. This is what is known as fitness landscape. And there is a host of literature on how to analyze landscape. That is why it is known as fitness landscape analysis. Okay, so you may have local optima, global optima, plateaus can be there. Plateaus means a region with constant or nearly equal objective function value. Okay, yeah, so this is the visualizing the landscape. All right, so we will just move to the today's slides. So today's idea is to talk about local search, then we'll move on to simulated annealing. We will talk about Tabu search, and if we have time, we can go to variable neighborhood descent. By the way, this variable neighborhood descent is not very difficult to understand if you understand local search, and yeah, so it is not very difficult to understand. Okay, so I have moved this local search idea, not idea, topic from today, yesterday to today, and this is the tentative schedule till now. I don't know how much we'll able to cover. Let's see how we proceed. Okay, all the resources will be available here, and this is the reference book I'm using. And I have added my LinkedIn profile link. If you want to connect with me, you can go to this link and send me a connection request. All right. Okay, so initial solution. So every metaheuristics require at least one or more than one initial solution to start with. It may be feasible, it may not be feasible, but the metaheuristics we will talk about right now requires a feasible solution to start from. What you can do is you can either generate, so since we are working with single solution metaheuristic, we will talk about generating one initial solution. When we go to population based metaheuristic, then we'll see what to do. Okay, so to generate the first solution, you can either randomly figure out a solution, or using a greedy heuristic, you can find the initial solution. If you have a very constrained problem, then you need to devise some strategy to obtain a feasible solution, and then also you have to devise move in such a way that your neighbors are feasible. Okay, so that becomes a different ideas to work with. What are the trade-off? if you um, if you start with a random solution, it is very quick, so getting a random solution is very quick, but it may require more iterations to converge. It may, by the way, it is not always true that it will require more iterations to converge. It may require more iterations to converge. Greedy heuristic, better initial solution, and may converge faster, and we don't know that if it is the global optima or the local optima. It will converge, but we don't know that convergence if it is a local optima or a global optima. You can mix both. You can devise a heuristic which randomly does something and greedily does some other thing. So there are many things to play with. For a TSP, you can just imagine we can just use any random permutation to start the search, or we can use a nearest neighbor greedy solution to start the search. Key takeaway: the choice of the initial solution impacts the efficiency of a meta-heuristic. A hybrid approach may be better. It is often better. We don't know what will work. You have to actually do and see, because problem property changes many things. So you have to go through your problem and see what will work and what will not. Any questions? All right. So I'll proceed. Local search. So what it does is it maintains a single solution and moves to the neighboring solution. It provides good enough solution. This is the idea of all meta-heuristic. It provides good enough solution while conserving computational resources. So local search is designed in such a way that it is not very computationally expensive. Okay, we will see how local search works by an example. Before that, we'll see the template of local search algorithm. So what it will do is it will have a initial solution. It will start from an initial solution, and it will, around that solution, it will generate its neighborhood. Inside the neighborhood, it will explore the solutions inside the neighborhood, and it will pick the solution which is, so it will explore the entire neighborhood. So suppose S is the initial solution and its neighborhood is n of S. This is the set of all neighbors of S. It will explore the entire neighborhood and pick the solution with the best objective function value among all its neighbors. So suppose it is S dash. And again, for S dash, it will generate its neighborhood and pick the solution among all the solutions in its neighborhood, the best solution. If that best solution is better than S dashed, then it will move to S double dashed and so on and so forth. So it will move from one solution to the other, improving the objective function in every iterations. So we will start with S naught and we will take S as S naught, and we will do a while loop until the termination criteria is met. We will talk about termination criteria. We generate the neighbors of S. If there is no better neighbor in this neighborhood N of S, no better neighbor means, so if you have a minimization problem, the objective function of the neighbors are not better than S. And if you have a maximization problem, the objective function value is not more than the objective function value of S. If it is not the case, if it is the case, then that you don't have a improved solution, you just stop the search and come out of the while loop. Otherwise, you move to that solution. You take that solution S dashed and you update S as S dashed and then generate its neighbor and then do the thing. So you can see it's a very simple idea. You just, so we can use this diagram, by the way. To suppose randomly we started over here, not exactly, let us take it here. So suppose we started over here. This is my initial solution S naught. We will generate its neighbor. So suppose this is the neighborhood of S dash S naught, and we see that this is the best solution in its neighborhood. So we'll move to this solution, and in this way our search will take us over here. Suppose the initial solution was this, S naught was this. So it will take us to this local optima. Okay. So this is how local optima works. It is highly sensitive to the initial solution you give. Is that all right? Any questions? Okay. I see a question. Just a minute. How many neighbors around the point? Okay, so what you will do is, so I was giving you an example. What you will do is, suppose you have a traveling salesman problem. That is what I was saying. And we have a permutation. So suppose it is a n city problem. So you have a permutation of n cities. And how many neighbors? So you say, suppose you have a swap neighborhood. Swap neighborhood. So what you will do is you will pick two neighbors and then exchange its position. What you will do is n of s will be set of all possible neighbors. How many soever you can do. You do all those and obtain the neighbors that will become its neighborhood. Local search explores all the neighbors in that neighborhood. So you exhaust the neighborhood. You can improve this, but this is the most vanilla form, most original forms, most classical form of local search. You obtain the neighborhood, all the neighbors in that neighborhood, and then you explore the whole neighborhood and pick the best solution. If that solution happens to be better than your current solution, move to that solution. Okay. So start with an initial solution, generate the neighbors using swap neighborhood, move to a better solution, repeat until no improving neighbor is found. Is it all right? Did I answer your question? All right. Thank you. Okay, so I have taken just a random example. It is just a 5 city problem. The initial solution is this. I obtained its objective function value, which is 25. Now I will generate all possible. My pencil is not working properly. Just so you generate all possible neighbors and then you pick the best among them. This is the classical local search. Okay. You can have another thing which is best improvement local search. Just a minute. One is best improvement. Best improvement local search. Just bear with me, my pencil is not working properly. Okay. What it does is you have a solution S, you start generating its neighbor one at a time. You generate its neighbor one at a time. Once you have obtained a better neighbor, just move to that neighbor. So you will not explore the whole neighborhood in such cases. Okay, so that is the idea. You're just saving on computational time with the uh, uh, inaccuracy that you are not going to the best solution. You may just go to another solution which is not the best among its neighbor in that neighborhood, but you are saving on computational effort. You are not required to search the whole neighborhood. In the iterations of generating its neighbor, you just check whether that neighbor is better than the current solution or not. If it is so, then move to that neighbor. That is known as best improvement local search. Move to the first improved solution. Just you don't need to exhaust the neighborhood. So that is what I will do in this example. So I have a solution, initial solution whose objective function value is 25, and I generated the first neighbor. So I'll come here. I generated the first neighbor. It has an objective function value of 30. I generated another neighbor. It has an objective function value of 27. I generated another neighbor. It has an objective function value of 19. And since it is the first improved solution, I will move to this solution. Now what I will do is I had S. I moved to S dash. This has an objective function of 25. This has an objective function of 19. Now I will generate its neighbor and I will see whether I'm getting an improved solution or not. I tried to do all, I obtained its neighborhood, I obtained all the solution and I saw that there is no better neighbor and therefore this is my local optima. I don't know if it's my global optima, but this is my local optima. Okay. So this is a very crude example, not a complete example, just to give you an idea what is happening. Is it clear? Is it clear? Okay. So we'll move forward. Selection of neighbor. So this is what I was saying you. Best improvement. It selects the best neighbor that maximally improves the objective function, evaluates all possible moves exhaustively. Advantage, ensures best possible improvement. Disadvantage, computationally expensive for large neighborhood. If you have a very large neighborhood, what do you mean by very large neighborhood? So suppose for a traveling salesman problem with a permutation representation, you are working with k opt. So we talked about 2 opt, you can have k opt. And in such cases, the neighborhood becomes large. So for large neighborhood, this is expensive. Or for example, you have the n city problem. The n is very large, 1,000 cities or 2,000 cities or 3,000 cities. So exhausting the whole neighborhood, even for swap moves, will be difficult. It will be large. The neighborhood will be large. Okay. First improvement. Okay, I was saying best improvement. This should be first improvement. It should be first improvement. All right. First improvement local search. So first improvement, it selects the first encountered improving solution. The first solution you encounter, which is improving the current solution, you just move to that solution. Involves partial evaluation of the neighborhood. If you have obtained a better neighbor, just move to it. So it saves computational effort. It is faster and often produce similar solutions. So what it is observed is it often produce similar quality results. So it depends upon problem to problem. Random selection. So what happens is in random selection, you select a random improving neighbor. What it means is you exhaust the neighborhood or you are when you are doing it, you select randomly whether to. So what I will do is I have a neighborhood n of s. I systematically generate its neighbors, right? So first, no improvement. So first solution is no improvement. You say whether I will select it or not randomly. Again, no improvement. You say whether I will select it or not randomly. So that is what random selection is. Once you have an improved solution, you can use first improvement strategy to move to that solution. If you remember, in our last class, I was talking about intensification and diversification, and I skipped it. I told you that we will discuss it later. So this is where the idea comes: intensification and diversification. All right. So what is intensification? Intensification means focusing on searching the vicinity of high quality solution. So what we are doing is, in local search, I have a point, I move to its best neighbor. Again, from that point, I move to its best neighbor. From that point, I move to its best neighbor, and from that point, I move to its best neighbor. I'm just focusing on the region of high quality. It is not exactly high quality solution. It focuses on the region where you know the solution quality is better. So that is what intensification is. Your search is focusing on regions of good solutions. It exploits known good areas in the search space of to refine the solution. So you are likely to say that I know that this is the area of good solutions. Let me explore that region only. I will ignore other regions. Local search is an example of a algorithm which only does intensification. It will only explore regions of good solutions. Local search only does intensification. What is diversification? It ensures exploration across the search space to avoid local optima. What it will do is, it will not only focus on the region of good solutions, it will try to move to other regions as well to see whether I'm skipping some regions of good solution. So that is what diversification means. You look into more areas in your search space. Intensification just means I'm focusing on some region, and diversification means focusing on many more other regions, unexplored regions. How can we do this? We can introduce randomness, or we can restart the local search multiple times. If you restart the local search multiple times, so suppose you started here, you came over here. You started over here, you came over here. You started over here, you came over here. By doing random restarts of local search, you can do diversification. Simulated annealing also has diversification. We will see how it does diversification. A genetic algorithm has also its components to do diversification. Classical local search doesn't do diversification. You can modify classical local search to do diversification. Okay. Effective metaheuristics balances between intensification and diversification to achieve optimal solution. So what your idea should be is, at the beginning of your search, you should diversify more and more. But as your search is maturing, as time is passing on, you should focus on intensifying, because you have explored many regions of the search. You will have a good idea which areas are lucrative areas. Move to those areas and do intensification in those areas. Good metaheuristic balances between intensification and diversification. I will repeat again. At the start of your search, do diversification. And when you have a good idea about your search space, then you do intensification. I see a question over here right now. How will you know what are good solution regions? So for suppose you are doing, okay, so I will answer this when I go to genetic algorithm. So you will know an idea. By the way, uh, solutions, good solution regions, you can think about it like that. The solutions which have lower objective function value might have regions of other solutions which have lower objective function value. So what it is so we try to construct our landscape in such a way that there are big basins, big local optimas. In such a case, diversification is not it is not very much required. So you don't need to do a lot of diversification. If your landscape is very multimodal, a lot of local optimas are there, then diversification will be required a lot. And how do you know which are good solution regions? So once you do lot of diversifications, you will get idea this solution, these solutions are there with lower objective function value for a minimization problem. I will go to those solutions and find its neighbors and search those regions. So this is how we can do intensifications in those regions. Did I answer your question? Genetic algorithm has some techniques of doing diversification first and then doing intensification. We will see that. But today we will see this diversification and intensification in simulated annealing. which means intensification follows diversification. Yes, most of the cases. In most of the cases. You can do that simultaneously as well. Genetic algorithm does that simultaneously. In single solution metaheuristic, this is the case. First we diversify and then we intensify. How to select which operator which yield better solution space. So that is what you have to do when, so what you will do is you will go to the literature and see how solutions are represented for your particular problem. What moves are used. You should use similar moves, right? So to get an idea of the landscape, you typically you should explore the whole search space. Then only you will have an idea of your landscape. But that is not feasible. So what we do is sampling. We do sampling and then we get idea of the landscape. By the way, landscape analysis is a difficult task to do. Okay. So I will, it is very difficult to answer what will your landscape look like. You have to go to the literature and see what people use, what people report. Okay, this representation is better for your solution. For example, yesterday I told you for traveling salesman problem, 2-opt is a better move than this swap, right swap. And for scheduling problem, 2-opt is not a good move. So these are comments because it comes from the landscape analysis. For scheduling problem, 2-opt gives a very rugged landscape. A lot of local optimas are there. But 2-opt used for traveling salesman problem is a very good, the landscape obtained is very good. Is it clear? Did I answer your question? Okay. All right. Escaping from local optima. So we saw that local search have a tendency to get stuck in local optima. How can we avoid local optima? So here are, okay, so we have local search algorithm. It is efficient and easy, converges quickly, but can get stuck in local optima. Highly sensitive to initial solution. It is very sensitive to initial solution. And it does not guarantee, by the way, no heuristic guarantees finding a global optima. So this is very generic. Strategies of escaping local optima. So let me go to this, what should I say, figure, where I have taken it from the book, the same book I am referring to. So what are the strategies of improving local search or escaping from local optima? So first is iteratively starting with different solutions. So we saw that for local search, if we start iteratively at different solutions, we may converge to different local optima. In such cases, we can employ this strategy, iterative start of local search. Okay, restart a different initial solution. The second idea is accepting non-improving neighbors. So when we saw local search, we saw that it only moves towards the steepest descent. I am here. I will always move this side. I will never move this side. So what this does is, if you are here, you will always go downhill. You will always go downhill. You will never go this side. But if you go this side, you will see that you can go to the global optima. So this is the idea of accepting non-improving solutions or non-improving neighbors. If you do this, there is a chance that you may go to the global optima. And this is what simulated annealing and Tabu Search tries to do. It accepts non-improving solution and it tries to move towards global optima. All right. So accepting non-improving moves. Another is modifying the neighborhood structure. So what we can do is we can try to modify the landscape of the problem. The landscape of the problem can be modified using, so how do we obtain the landscape? The landscape is actually obtained from the representation and neighborhood generation operator. So you can try to change the neighborhood generation scheme using different neighborhoods. That variable neighborhood search or variable neighborhood descent is an example of using various neighborhoods while searching. So when you are searching, don't search in just using one neighborhood operator. Use various neighborhood operators, generate different kinds of neighborhood throughout your search, and then you will get different landscapes, and you may go to the global optima. Another thing that affects the landscape is the objective function. So you change the objective function, you modify the objective function in such a way that it is less rugged. Okay, so that is the idea. Either modify the landscape, either modify the objective function or modify the neighborhood structure. So these are ways of escaping local optima. Is it all right? Is it all right? Okay, I have. Yes, okay. Simulated annealing. What is simulated annealing? You see, local search is a deterministic algorithm. If you start from the same, if you start with the same initial solution, you will get the same final solution. It is deterministic in nature. If you give the same initial solution, you will get the same final solution. Simulated annealing is a stochastic local search algorithm. It allows worsening the objective function value with some probability. Indirectly, it is saying it accepts non-improving solution. So this is an indirect way of saying that we are allowing non-improving solution. Help escape local optima and delay premature convergence. It is memoryless. So yesterday we talked about some algorithms may use memory. So this simulated annealing is memoryless. Local search is also memoryless. Tabu search has a memory, and we'll talk about tabu search today. Analogy to physics. So simulated annealing, the origin of this comes from annealing process of metals. So metals are heated at a high temperature, and then it is slowly cooled. This cooling allows a restructuring of the grains of the metal and makes it stronger. So optimization view. So what we are doing is, with high temperature, so if you take the analogy of metals at high temperature, the atoms move very randomly, and as the temperature cools, the randomness decreases. So that will be our idea. At high temperature, we will let the search explore randomly. It will explore at random regions of the search space. As the temperature cools, we will move to more controlled manner of search. Okay, so this is the idea. As the temperature decreases, the randomness of searching the neighborhood decreases. Okay. So it is inspired by metallurgy. The core idea is begin with high temperature that allows exploration of the search. So exploration is diversification. Okay. So at high temperature, we allow exploration of the search, which is diversification. As the temperature decreases, we do intensification. So this is how simulated annealing tries to balance between diversification and intensification. Gradually decrease the temperature, reducing the likelihood of. I will talk about what this means. Okay. So what we do is, before that, let me come over here. Yes. So what we will do is, we will start with an initial solution S naught and of initial temperature T max. So this is a high temperature. All right. And then what we'll do is, we will generate the neighbors of S. So let me take a page. So this is S, and we will generate its neighbor. Now that this neighborhood is N of S. Suppose S dashed belongs to N of S. If S dashed is better than, then move to it. Okay. So if S dashed is better than S, then we move to it. If S dashed is worse than S, then there's a probability that we'll move to S dashed. Then it is we will not reject it. In local search, what we do is we reject S dash when it is worse. But in simulated annealing, there is some probability that will move to that S dash. And this exploration of neighborhood is random. In local search, you can have a systematic search in the local neighborhood. So suppose for a permutation representation, you are using shift neighborhood. What you are doing is you are picking this and shifting it to first position, then second position, then third position, and fourth position, then fifth position. Then you are taking the second item and then seeing this position, then this position, then this position, then this position. This is a systematic way of generating the neighborhood. You have a system that this is how the neighborhoods will be generated. But in simulated annealing, we generate the neighborhood randomly. I'll pick this and I'll move it to this position. Let me use another color. I'll pick this and move it to this neighborhood. In the next iteration, I'll pick this and I'll move it to this position. So it is random generation of neighbors. And in doing that, we will check this. If the new neighbor is better than the current solution, I will always move. There is no randomness. But if it is worse, then I will move with some probability. What is that probability? That probability comes from exactly what it is used in metallurgy. So delta E is the difference in the objective function value of the neighbor and the current solution. If this is less than equals to 0, I will move to that neighbor. It shouldn't be equality. You can just forget about equality. What we'll do is we will say it is less than 0 and greater than equals to 0. Okay. I'm just moving the equality from the above to the below. So I'm saying that if the neighbor is better, strictly better, I will move to that solution. If the neighbor is either same or worse, there is some probability that I'll move to that neighbor. Okay. So if the neighbor is better, always move to that neighbor. But if the neighbor is worse or has the same objective function value, this is the probability function I'll use. Delta E by T, e to the power minus delta E by T. What is T? T is that temperature we are working with. And we will start the search with a high temperature and will gradually decrease the temperature. Moreover, if this delta E is large, the probability of acceptance is low. So we are not just always moving to a worse solution. We are actually indirectly seeing how worse is that solution. This probability decreases with increase in delta E. The higher the delta E, the worse is that solution, the less is the probability that we'll move to that solution. So the probability of moving to a worse solution is directly proportional to delta E. The probability of moving to that solution is directly proportional to indirectly proportional to delta E. It is indirectly proportional. It is indirectly proportional to delta E. The higher the delta E, the less is the probability. And the probability of moving to that solution is directly proportional to the temperature. The higher the temperature, the higher is the probability that we will move to that non-improving solution. Is it all right? Any questions? Okay. So this is the probability function which is generally used in simulated annealing. And I have given you one example over here just to show you. So I have a solution S, and suppose one S dash has a delta E of 1, second S dash has a delta E of 2, and third S dash has a delta E of 3. So you see, as temperature increases, not temperature, as delta E increases, the probability of acceptance goes down. At a temperature of 10, the probability of acceptance goes down from 90.90% to 74%. At a temperature of 5, the probability of acceptance goes down from 82% to 55%. So as delta E increases, the probability of acceptance decreases. And this is reverse for temperature. As temperature increases, the probability of acceptance increases. It increases from 0.37 to 0.90. Okay. So this is the algorithm of simulated annealing. What we are doing is, so we have a initial temperature, and at that temperature we will do, at that temperature, just a minute, at that temperature we will generate the neighbors of S randomly, random neighbors of S. We will obtain the decrease in objective function value. If it is less than equals to 0, okay, equality is there. But equality doesn't matter a lot. Okay. If it is less than equals to 0, we move to that neighbor. Else, accept this worst neighbor with this probability. And we do this until some criteria is met, some equilibrium criteria is met. Once this loop is completed, we update the temperature. So I'll tell you what we are doing because it is important to understand. So at temperature T naught, suppose not T naught, any temperature T, we will run a loop like a local search with probabilities of acceptance. So suppose I have S, I move to S dash, then I move to S double dash, then I move to S triple dash, and so on and so forth. When this search matures, that is equilibrium is obtained, then we update this T to T dash, and then we repeat the process again. We have S, we move to S dash, then we move to S double dash, then S triple dash, and so on and so forth. Once equilibrium is obtained, then we update the temperature T double dash and repeat the process again. So this is how cooling is happening. At one temperature, we perform some operations and then again we decrease the temperature. So this is why there are two loops over here. The first loop is for the temperature and the other loop is for a given temperature, perform some number of iterations. And what does this equilibrium condition means? We will see. I have a slide on equilibrium condition, but this stopping criteria is on temperature. So what can be one stopping criteria? We can define a minimum temperature. If the temperature reaches this point, stop the search. Okay. If the temperature reaches that point, we can stop the search. What can be this equilibrium condition? So suppose I am doing this number of this local search and I am seeing that I am visiting the same solution again and again for some number of times. It means that at that temperature, I'm not improving the solution. So an equilibrium is obtained, maybe change the temperature and then we'll move to some other neighbor. So at a given temperature, I have done some number of local search and then I see that I am always stuck with S triple dash. Always S triple dash is there. Always S triple dash is there. It means that some kind of equilibrium is obtained. Now it's time to change the temperature. When I change the temperature, it may happen that the search will go on for some number of time and then I'm stuck with some solution for some number of iterations. Then it's time to change the temperature again. And this is how the search progresses. Is it clear? Is the idea of simulated annealing clear? It's just that we are allowing non-improving solution. That is the core idea of simulated annealing. How you do it, it is up to you. This is not written that you have to apply simulated annealing like this. You can change this in some manner or the other. The idea should be you should allow non-improving solutions. You can change the probability function as well. It is up to you. You can define your own simulated annealing. The core idea should be you are using local search as well as allowing non-improving solution. Okay. So then at the end of this algorithm, we would have lot of solution in our bag. Some solutions are with some probability and some are not. So my question is, how can we select the, no. So what we are doing is you got it wrong. So suppose I obtained S triple dash. I will take this S triple dash over here. So it is actually starting from S triple dash. And this it will be S4, S5, and so on and so forth. So the solution from the top level will go down to it will become the current solution at the bottom level. We are not getting multiple solutions. And by the way, throughout the search, we store the best solution encountered. My pencil is not working properly. Throughout the search, we will store the best solution we have seen, such that when the simulated annealing terminates, I can give you that this is the best solution. And your question, what I understood is, from any temperature point, whatever local optima I am getting, I will pass it down as the current solution at the next temperature. So it is not that we are getting multiple solutions, we are just refining the same solution again and again. So if you see like this, if you just take a simple landscape. So suppose we are here and we came here, then we came here, then we again went back here, then we went back here, then we come here, then we come here, then we come here, then we come here, we got stuck. But this, since this is simulated annealing, we jumped over here, then we jumped over here, then we came back here, then we jumped over here, then we jumped over. So we are always working with one solution. This is single solution metaheuristics. We don't have multiple solutions. But in this process, you see, till now, till this point, this is the best solution I have. I will store this solution until and unless I obtain a better solution than this. So suppose my search is coming on, and when I came here, I saw that this solution is better than this solution. So I will remove this as the best solution and keep this as the best solution. When I search again, I got this. This is my next best solution. So throughout the search, I am storing the best solution found so far. Is that clear? And I'm always working with only one solution. I'm not working with multiple solutions. Okay. All right. So moving on, how to choose initial temperature? So you see, initial temperature shouldn't be very high. If you take a very high temperature, what will happen is the probability is actually equals to e to the power minus delta E by T. If you take a very high temperature, the probability of accepting the move is very, very high. So suppose it becomes 99% probability, pick that solution. So it is just a random walk. You're just randomly sampling different solutions in the search space. So you shouldn't take it very high. You shouldn't take it very low either. If you take it very low, then it boils down to just a local search. You're not allowing any non-improving move. You should select initial solution very wisely. Okay. Cooling schedule. What is cooling schedule? You see in this algorithm, there is this function GT. This is the cooling schedule. It tells you what will be your next temperature. This function is the cooling schedule. What will be your next temperature? Okay. So you can take a geometric cooling schedule that at each iteration, my temperature will be reduced to 90% of what it was, 99% or anything. You can take it in this form. You can take a linear cooling schedule that after each iteration, my temperature will decrease by 2 units or 3 units or something or the other. You can take a logarithmic form. You can do adaptive as well. So based on your search progress, you can define a function depending upon the objective function value of the solution. So something like the temperature depends upon the delta E of the start of the. So over here, I will start. I will say it is E1. And when this terminates, it is E2. So this delta E, the change in the initial solution while giving to the at a temperature, and when the search matures, I can obtain delta E. Depending upon this, we can define a cooling schedule that it changes depending upon how well the objective function improved. So there can be multiple ways. You just have to see that your cooling schedule is such that you have both kinds of properties in your algorithm: diversification and intensification, exploration and exploitation. This is also known as exploration. Diversification is known as exploration, and intensification is known as exploitation. Is it clear? Any questions? Okay, so I'll proceed. Stopping condition. So this stopping condition is the stopping condition of the simulated annealing, this stopping condition. So I told you one stopping condition, that it has reached a minimum temperature. The lowest temperature has been recorded. No improvement for some number of iterations. You are not seeing any improvement for some number of iterations. So you can just stop. What does this mean is, for each temperature you are doing some iterations, right? So suppose you did some number of iterations and you saw no improvement. Again, for the next temperature, you did some number of iterations, you saw no improvement. So you can stop on depending upon that. I am doing some number of iterations and I am not seeing any improvement. So there can be multiple criterias of stopping. Okay. Advantage. Okay, I did not talk about equilibrium, so I don't have a slide over here, but again, this equilibrium can be anything. You can say that if I don't see an improvement for some number of iterations, let me stop. So that can be an equilibrium condition. See, this is just a template of simulated annealing. You can change it howsoever you like, but if you are defining a simulated annealing algorithm, the idea should be there is a local search, you are performing a local search, and in that local search, you are accepting non-improving moves. That's it. If you do that, it will be called as simulated annealing. You can just say, I will not have this loop, I will not have this while loop, just remove this while loop. At each temperature, I will just do one local search. I will not have this while loop. At each temperature, I will generate its neighbor. I will check and I will move to that neighbor if it is if it is improving, and with some probability, I will move to that non-improving solution, and I'll update the temperature. You can define a simulated annealing in that way also. You don't need two loops inside a simulated annealing to be strictly label it as simulated annealing. The idea of simulated annealing is just that you are allowing non-improving moves using this temperature part. Okay, so the temperature part is coming from the probability is taking from that temperature. That idea should be there, and then it will become simulated annealing. You are starting with a higher temperature, and using that temperature, you are defining probabilities of accepting non-improving solutions. That's the idea. Is it clear? Okay, I suppose it is clear. Advantages and disadvantages of simulated annealing. So what are the advantages? It is simple and easy to implement, can escape local optima because it accepts worst solution, works well for a wide range of optimization problem. Limitations, performance depends upon the cooling schedule. If you decrease the temperature too fast, then you may get stuck in a local optima. These are the parameters of your algorithm. Okay. Require a tuning of parameters. That is what I'm saying, that your initial temperature should be appropriate, your final temperature should be appropriate, your cooling schedule should be appropriate. Convergence can be so for large problems. So if you have a large problem, convergence can be slow. Is it clear? We'll move to Tabu Search now. Any questions? You can ask questions. I can wait for 2-3 minutes if you have some kind of questions. All right. So let us proceed to Tabu Search then. Simulated annealing was a stochastic algorithm, but this is a deterministic metaheuristic. If you give the same initial solution, it will give you the same output. If you don't introduce some kind of stochasticity in tabu search, the vanilla version or the classical tabu search doesn't have stochastic features. It was introduced by Glover in 1989. Okay. By the way, there are tabu search with stochastic versions, but classic tabu search doesn't have any stochastic version, doesn't have any stochastic features. It enhances local search using memory to avoid cycles and escaping local optima. So if I go back to that classification, let me come. Yeah. So you see, the idea remains the same for simulated annealing and for taboo search, that we are accepting non-improving neighbors. In simulated annealing, how are we doing that? We are doing it stochastically, probabilistically. We are saying that, okay, this is a non-improving solution. Should we accept it or not? There's some probability of acceptance and rejection. Okay, so that is how simulated annealing works. Taboo search works in a different way. And moreover, in simulated annealing, we search the neighborhood randomly. So generating a new neighbor is random. But in taboo search, you can have a systematic way of generating the neighbor. You completely search the neighborhood. For taboo search, I'm talking about. You completely search the neighborhood. If you found an improved solution, you move to that solution. So just like local search, if you found a improved solution, move to that solution. Then again search the neighborhood, move to that solution. Like this, when you come to a local optima, in local search you are stuck. You cannot move anywhere else if you are talking about local search. But what taboo search does is, it says that if you are at a local optima and you don't see any improved neighbor, you move to one of the non-improving solution. That is what taboo search is doing. While moving to this non-improving solution, you store some features of your search process. What it will do is, it will help you not cycle back. Because if you are here and if you do local search, you are bound to come back over here, right? Since you accepted a non-improving solution, you move to a non-improving solution, you search its neighbor, you are bound to come back. So what taboo search does is, when you are at a local optima, you don't see any improved solution in your neighborhood, move to a non-improving neighbor. While moving to that non-improving neighbor, you store some features of your search. That feature can be anything. What move do you use to come to this non-improving solution? What was your local optima? We will see those features, what it is doing. When you store that and you are searching this solution's neighbor, you will not move to this solution. Why? Because we are asking your search to not move back. The taboo search will disallow cycling. It will not allow you to come back to that solution. And in this way, it can lead you to another um, local optima. Is it clear? Is the idea clear? Okay. So if it is clear, let me move to taboo search. Right. The key idea: explore the full neighborhood at each iteration. Can accept non-improving solution to escape local optima. Use a taboo list. So this is what the memory is. Taboo list. To forbid recently used moves or attributes. So suppose from a local optima of a permutation representation, say suppose this is the local optima A, B, C, D, E, and F. This is the local optima, and you did a swap of these two solutions. Once you did a swap of these two solutions, suppose you are storing this local solution. Suppose you are storing this solution. And where it will be stored? It will stored in the taboo list. That is what a taboo list is. Now, when you move this, you went to a non-improving solution and you are searching the neighbors of that non-improving solution. You will not come back because you have this solution in your taboo list. Your taboo list will say, hey, I have this solution. You are not allowed to come back to this solution. So this taboo list stores solution. But as you can imagine, if your search space is very, very large, storing taboo list and going through all the solution in a taboo list is computationally expensive. If you have hundreds and thousands of solutions in your taboo list, and when you are at a solution, you have to always check whether my new neighbor is in the taboo list. To do that, you have to go through the entire taboo list, and that becomes expensive. To avoid doing searching in the taboo list and wasting time, we generally store moves in the taboo list. So in this case, you see, we swapped the fourth and the fifth element to obtain a non-improving solution. So in my taboo list, I will store swapping fourth and fifth element. So from this solution, I will not swap back fourth and fifth element. So that is A, B, C, E, D, F. From this solution, when I generate neighbor, I will not swap fourth and fifth element. That takes care of the fact that I will not move back to my original solution. Is it clear? So taboo list can have recent solutions or can have recent moves. But you see, by disallowing this move, third and fourth, when I go to some other solution, suppose in that case, I swapped C and E. So I obtained A, B, E, C, D, and F. You see, since this 4 and 3 are in the taboo list, I will again not allow 4 and 3 to swap back. So it is a restrictive form of taboo list. If you're storing moves, you are restricting your solution space. Is it clear? So two things to take a note. First, if you store solutions, you will have to spend more time searching through the taboo list. Second, if you store moves, it will ensure that your taboo list is not very large, but it will make your search space smaller and smaller and smaller. So the next thing, how to avoid that, that comes from aspiration criteria. It overrides the taboo restriction when beneficial. So you see, from this solution, since 3 and 4 is in the taboo list, I am saying don't move back 3 and 4. But suppose moving back 3 and 4, doing the swap of 3 and 4. So from this, if I do A, B, E, D, C, F. Suppose if I do that, if I do the swap of 3 and 4, I obtain a better solution. Suppose this was objective function of 100 and this is 90. In such cases, I can override my taboo restriction. That is what aspiration criteria says. You can define some criterias that if a decrease in an objective function of 10% is obtained, I will not overwrite, I will ignore my taboo moves. I will accept that taboo move. Is it clear? Any questions? So you see, have a memory in this search. Some kind of memory is being maintained. Any doubt? Okay, there's a question. Is there a variable which tells about number of the latest solution memory should be? Is there a variable which tells about number of the latest solution memory should be? I did not understand your question, but if you're asking about the size of the taboo list, then yes, it is a decision variable. You have not a decision variable, it is a decision you have to take. It is a parameter. So that's size of the taboo list, you have to decide how large the taboo list should be. Suppose you say that I will not keep more than 100 taboo moves. So what it will do is it will remove the oldest taboo move once the size is exceeded, so that things can be taken care of later. For solutions also you can do that. So suppose you can say I will not store more than 300 solutions in my taboo list. What it will do is, as the 301 solution come, it will remove the first solution, but there is a danger of cycling. If you do that, there's a possibility that cycling may occur. Over here also cycling may occur, by the way. If you restrict memory, cycling may be occurred. You may move back to the same solution and whatever you did will again happen again. Is it clear? Okay. All right. Next. Motive. Yeah, we have talked about local search moves only to improving neighbors, get stuck in, may get stuck in. may get stuck in local optima. Simulated annealing, except words move probabilistically, still memoryless may revisit the same solution. Uh, Tabu search accepts the best admissible move. Admissible means allowable move. Okay. Even if it is worse, use memory to prevent returning to the recently visited solution. Directs the search dynamically through short term, medium term, and long term memories. So, this tabu list is a short term memory. This tabu list is a short term memory. What is a medium term and a long term memory? We will see as we talk more about tabu list. Okay. Tabu list, nahi, tabu search. Is it clear? Okay. So, this tabu list is a short term memory. You can say that for n number of iterations, I will store the taboo moves. Otherwise, I will remove all the taboo moves. Those comes under aspiration criteria, by the way. Not exactly aspiration criteria, but you are defining the taboo list in such a way that if I store some number of moves and if I complete k number of iterations, I will remove. If a solution is there in the taboo list for k number of iterations, I will remove that solution from the taboo list. If I have a move for k number of iterations in the taboo list, I will remove that move from the taboo list after k number of iterations. Is it clear? Just let me drink water. If you have questions, you can ask. Okay, so short-term memory, we talked about this taboo list, prevent cycling and avoid revisiting recently explored solution. The taboo list can store full solutions, but this is expensive. It can store recently applied move, attributes of a move. So recently applied move was, so over here, a recently applied move was swapping E and D. You can store that as well. So over here, it is not swapping 4 and 3. You can say, I will not swap D and E wherever they are. It can be in the first position, third position. So that is attribute recently applied moves. I swapped 3 and 4, not 3 and 4. I swapped D and E. I will not swap back D and E. Attributes of a move. I will not swap the elements in the position 3 and 4. Solution components. So for example, uh, if I removed an edge from a traveling salesman problem, if the edge was A to B, I will not bring back A to B. I will not bring back A to B. It has solution components. Is it all right? So these are the few things that can comprise your taboo list. Taboo tenure. So this is what it means. The number of iterations, the move or the attribute remains in the taboo list. You can say that my move will be in the taboo list for k number of iterations. That is known as taboo tenure. Clear? Using attributes may forbid moves, but yeah, so this talks about if you store attributes, this is what we saw here, right? Um, if you store attributes, it may forbid some good solutions, and it may so it says move does not actually cause a cycle. So what it is saying is storing moves can make it too restrictive. So you are not allowing the two moves, suppose element in the fourth and the third position to swap back. It is too restrictive. Okay, so this is what it is saying. Okay, and the other factor is a good move may be marked as taboo. How do we allow exceptions? So this is the idea of aspiration criteria. If you have said that I will not move back 4 and 3 again, but if you see that I have a solution which is better than my existing solution, what should we do? What should we do? How do we allow this exception that comes from aspiration criteria? Okay. Before that, I have a slide. Let me see. Okay, it is an example. So it says that I have a permutation problem, permutation representation problem where I am talking about swap moves. I have a solution pi and I applied the move swapping I to j. I will store the reverse move j to I. So for example, in this example, I swapped d and e. So I will store e and d. I will not swap back e and d. That is what it is saying. So I will store this uh, I and j, and then I will say use multiple tabu list. So I will not talk about this multiple tabu list. This is an example of storing tabu list. Okay. Aspiration criteria. Sometimes a taboo move is actually desirable. So you can have aspiration criteria predefined. Some examples of aspiration criteria: a move generates a solution better than the best so far solution. Till now, whatever solution you have, if you see that your forbidden move is actually giving you a solution the best you have obtained so far, obviously you should go to that solution. Why would you reject that solution? So you should overwrite your taboo list, or not taboo list, taboo move. Or if it satisfies some problem specific quantity. So suppose you're saying that if the objective function decreases by 10%, I will move to that solution. I will not bother about my taboo list. Some kind of problem specific quantity. Okay. Effect: prevent taboo list from being overridden, prevent taboo rules from being overly restrictive. So you are not being very, very restrictive. By the way, this comes because we are not storing solutions. If we are storing solutions in the taboo list, then the question of aspiration criteria doesn't come, because we have solutions stored in my taboo list. If we are coming back to that solution, we shouldn't allow to our search to come back to this solution. Aspiration criteria is there because we are not storing solutions in my taboo list. We are storing moves or some features of the move. That's why aspiration criteria is there. Okay. So this is needed when you are not storing solutions in your taboo list. Ensures high quality improvements are never blocked. Only admissible moves enter the next iteration. What is an admissible move? The move that is allowed, the move that is not taboo or satisfies a aspiration criteria. So it is not taboo or satisfies the aspiration criteria. Is it clear? Neighborhood exploration, best move selection, taboo list, aspiration criteria. We have talked about all this. Is it clear? This is the algorithm of taboo search. Before that, any questions? No questions. All right. So we have an initial solution is we initialize the taboo list. Suppose the initial taboo list is empty. Some stopping criteria, by the way, defining stopping criteria for our metaheuristic algorithm is also very, very important. You shouldn't just say ki my time limit is my stopping criteria. That will be your stopping criteria, but you should define better stopping criteria. For example, if my solution doesn't improve for some number of iterations. So in taboo list also, if my solution is not improving for k number of iterations, I will just stop the search. I will assume that my search has matured. Other criteria can be if my solution is oscillating between two features of my solution. So suppose you have designed a metaheuristic which works with infeasible solutions as well. So your stopping criteria can be if my algorithm, is stuck between infeasibility and feasibility. That is, my solution is going from infeasible solution to feasible solution uh, consecutively for some number of iterations, just stop the search. So these can be some stopping criteria also. All right. So definition of stopping criteria, defining stopping criteria for our algorithm is very important. There should be good stopping criterias. So what we'll do is we will generate the neighbor, find the best solution in the neighborhood. And if your solution do not find any best solution, then you do the aspiration check, aspiration criteria, and then you find the best admissible neighbor. So when I'm saying admissible neighbor, it means that either it is non-taboo or it is taboo but satisfies the aspiration criteria. That is what it means by admissible neighbor as dashed. non-taboo or aspiration criteria holds. Move to that solution, update the taboo list. In each iteration, we'll update the taboo list and then the search cycles back. Once the while loop is completed or the termination criteria is met, I will return the best found solution. Clear? Okay. Now I was talking about Tabu Search has short-term memory, medium-term memory, as well as long-term memory. So we will see what this medium-term memory and long-term memory is. Okay. Just a minute. Okay. So medium-term memory. So you see this search, it doesn't talk about medium-term memory or long-term memory. How will we use this medium-term memory and long-term memory? What we can do is after this while loop or in between this while loop, we can have another while loop. We can, my pencil is not working properly. Okay, so please bear with me. We can have another while loop. We can have another while loop. What we'll do is we will complete this. Once the inside while loop stops, we can restart the Tabu search. So just like simulated annealing, not just like the simulated annealing, but we'll have two while loops. The outer while loop will do something else, but the inner while loop will actually do the Tabu search. What will be the outside while loop do? That while loop will do restart of the Tabu search. It will restart the Tabu search. And why are we doing that? So for example, in local search, we are saying that if we restart the search, we may go to some global optima. From local optima, we may go to the global optima. So restarting is beneficial. That is the idea of Tabu search. What we'll do is we will store. So while doing the Tabu search, suppose in the first iteration of Tabu search, we are working with a traveling salesman problem. And we saw that in this traveling salesman problem, there are some edges. So I'll have a matrix of n cross n. So 1, 2, 3 till n. And again, n cross n matrix, right? So in this matrix, I will see that for this entire taboo search, I saw that some number of edges are repeated many number of times. Many solutions has this number of edges. So I will store values of those um, I will say again. So suppose the edge 2 to 7 that was encountered 20 number of times in this Tabu search. When I was doing this Tabu search from one solution to the other, the edge from 2 to 7 was encountered 20 number of times. Similarly, the edge from 2 to 1 was encountered one number of times throughout the entire Tabu search. I will store this kind of details, and these details will become my long-term and short-term memory. How will we use it? You see, when an edge is repeated some number of time, we can restart the Tabu search, enforcing that this edge is there in the solution. So this is intensification. We are trying to do intensification. So medium-term memory is all about intensification. It focuses on the promising regions of the search. It will restart the best solution, fixing a highly desirable component. So if I see that my Tabu search favors the edge 2 to 7, I will fix my solution to have the edge 2 to 7 every time, and I will restart the search. So this is intensification. I will say that I think that my edge 2 to 7 is very, very cheap. I will make my solution with the edge always present. So this is intensification, and this is known as medium term memory. Okay, so it elite solutions best found so far. We will find their common features. What are the common features of the best solution we have found so far? We will use those features and then restart the search, and we will do intensification. Restart the search from the best solution by fixing the desirable component. We are biasing the move selection. We will say that do not always keep the edge 2 to 7 in my solution, biasing the search selection towards frequently appearing components. Instead of saying that always keep 2 to 7, you can say that there is a high chance of the solution to have 2 to 7, something like that. You can play with these details, but the idea is to move your search towards desirable components in your solution. Another is long-term memory. So what this is focusing on diversification. You see, when I was doing this, I saw that 2 to 1 was encountered just one number of times. Maybe it is in some other basin. So I'll show you basins and then you will understand. Suppose I have two big basins. In this search, the edge 2 to 1 is favored more. And in this search, the edge 2 to 1 is not favored more. So I was searching over here. I did intensification and I'm searching still over here. And I'm seeing whenever I don't see the edge 2 to 1. Let me enforce the edge 2 to 1. Maybe I can move to some other basin in my search. That is what diversification says. The purpose is to encourage the search to explore unvisited or rarely visited regions. It serves the long-term memory. Frequency of the component appearing in the past solution is tracked, and we restart the search using the component that are rarely used. It penalizes frequently used components. On the other way, you can say that I will not allow frequently occurring components in the objective function. You see, these are opposing ideas. This idea is saying I will allow the frequently features, and this says I will not allow frequent features. So you have to balance between the two. Diversification and intensification are very opposing ideas. So sometimes you have to do diversification, sometimes you have to do intensification. Strategic oscillation, I'll leave it out of the discussion right now. Okay. It prevents the search from stagnation and promote broader exploration. By the way, diversification is also known as exploration and intensification is also known as exploitation. Is it all right? So Simran was asking about this how we will know that which areas are promising areas and which areas should we do diversification. Did that idea become clear, Simran? Oh, okay, I'll assume it is clear. Yeah, yes. Okay. Okay, so short-term memory, it is the purpose is to prevent cycles. It is taken care by tabu list. Medium-term memory, the idea is intensification. It is also known as the recency memory or elite solutions. A long-term memory diversification, we have a frequency memory to keep. Okay, the idea is to balance between exploration and exploitation, intensification or diversification. Okay. Strengths and challenges. Strengths are escape local optima deterministically. So you see, we did not talk about stochasticity in any way in tabu search because this is the classical form of tabu search. It is flexible. It can use multiple neighbors and memory layers. So you can have a tabu search with only short-term memory. You know, don't keep long-term or short-term memory. You can just keep short-term and medium-term memory. That is, you can just play with it. But short-term memory is very, very important. That is where tabu list is there and tabu search has a tabu list. So short-term memory should be there. You can just think about whether to keep medium term and long term memory. Okay. uh, Effective on many large scale combinatorial optimization problem challenges. Many components have to be carefully designed. So what should be my size of the tabu list? What should be the tabu tenure? What should be my aspiration criteria? How should I keep my long-term memory? How should I keep my short-term memory? How should I use those ideas of intensification and many, many things to take care of? Sensitive to tabu tenure and memory parameters. Sorry. Okay. More complex than simulated annealing or basic local search. That's it. Okay. Then we will go to variable neighborhood descent. Just give me a minute. I had a call. I'll just talk and then I will come back in 2 minutes. So you can take a break of 2 minutes. We will start at 5:36. Okay. All right, I hope all of you are here. So this portion I thought I would not be able to cover. So what we have done till now is just I'll come back over here. Okay, I hope I'm audible. Yeah, I'm audible. Okay, so what we have done is we have completed local search, simulated annealing, and taboo search. We are over here, variable neighborhood descent. So we will complete this today. The idea is very simple. It is easy to understand. Just let me come back over here. So by the way, there are two similar, not similar, but the name is very similar. One is variable neighborhood descent and one is variable neighborhood search. So we are talking about variable neighborhood descent and not variable neighborhood search. Okay. At the end, I have a slide which talks about the differences between variable neighborhood descent and variable neighborhood search. But currently, we are only talking about variable neighborhood descent. So variable neighborhood descent is a deterministic local search. It is a deterministic algorithm, first of all, and it actually systematically explores multiple neighborhood structures. So if I come back to this, sorry, if I come back to this classification, you see, we are here. We are changing the landscape and we are using different neighborhoods. And this is variable neighborhood search, but we are talking about variable neighborhood descent. Okay. So variable neighborhood descent. The key idea is, so you see, we have talked about if the neighborhood structure changes, if you move, your move operator changes, your landscape will change, right? We have talked about this. So the idea is we will use different kinds of neighborhoods in the search. We will have two, three kinds of neighborhoods. So for a traveling salesman problem, I will use swap neighborhood. I will use shift neighborhood. I will use two opt neighborhood. I will use three opt neighborhood. These kinds of different neighborhoods I will create, and my search will explore all the neighborhoods. And then when it explores all the neighborhood, I will say that I have found the local optima. Okay, so this is how it will do. So for example, if my solution is this S and I explored neighborhood 1. So um, this was my landscape for neighborhood 1, and I saw that this is the local optima in neighborhood 1. For neighborhood 2, the landscape looked like this, and I saw that S is also a local optima for neighborhood 2. And similarly for neighborhood 3 also, I saw that this is my local optima for neighborhood 3. Once I have searched all the neighborhoods and I see that it is a local optima for in all the three neighborhoods, I will conclude that S is my this S is my local optimal solution. And this neighborhoods, we have different operators to create this neighborhood. Also, these neighborhoods may have different sizes. So what do I mean by size? You see, when we have a permutation neighborhood and I use shift neighborhood, I will pick a element and I will shift it to different neighborhood. So how many positions can one element go? It can go in n minus 1 position. And how many elements I can pick? I can pick n elements. So the size of this neighborhood is n times n minus 1. For swap neighborhood, I am picking two elements and I am swapping its position. So how many ways I can pick two elements? It is nc2, but since we can pick same elements in the two directions, so element 1, element 2, and element 2, element 1. So the size of the neighborhood is nc2 by 2. If I'm not wrong, maybe I'm wrong. Nevertheless, the idea is the size of the neighborhoods are different. For two opt, the size is different, and so on and so forth. So some neighborhoods can be small, some neighborhoods can be large, and some neighborhoods can be very, very large. So you are searching different sizes of the neighborhood. So your search space was this much, then it in the second neighborhood it increased, in the third neighborhood it increased further. So in a way you are trying to explore larger and larger neighborhoods as well. So that is the idea. Is it clear? Then we'll proceed. Okay. So a solution that is a local optima in one neighborhood may not be the local optima in another neighborhood. VND uses several neighborhoods N1, N2, Nk to improve the solution. Why variable neighborhood descent? it reduces the chance of being trapped in poor local optima. Since we are searching in different neighborhoods, there is a less chance of searching in poor local optima. We may go to a very good local optima. What do I mean by very good local optima? It is the solution quality is close to global optima, or it is the global optima. Alternate between neighborhood to explore richer search regions. It is simple, it is deterministic, and often very effective. Okay. So this is the algorithm of variable neighborhood descent. Before going through the algorithm, let me talk about how variable neighborhood descent works. So I have a solution, current solution S. First, I will search the first neighborhood N1. If I have found an improved solution, I will come back to N1. That means I will, if a solution S dash, which is better than S, then I will again start from N1. If there is no improved solution in N1, then I will search N2. If I found an improved solution in N2, then the search will circle back to N1. Okay, so in whatever neighborhood you are, if you found an improved solution, you will go back to the first neighborhood and search again. Why this is the case? It is because the neighborhoods are arranged in increasing order of size. So the size of N1 is smaller than the size of N2, and the size of N2 is smaller than size of N3, and so on and so forth. So the size of the neighborhood is increases. This is the order on how the neighborhood should be arranged. In any one of the neighborhood, whenever you encounter an improved solution, you go back to the first neighborhood and start again. If you found an improved solution in the first neighborhood, start again in the first neighborhood. If you found an improved solution in second neighborhood, the search will start again from the first neighborhood. If you found an improved neighbor in the third neighborhood, how will you find the improved neighbor in the third neighborhood? There is no improved neighbor in the first neighborhood. There is no improved neighbor in the second neighborhood. Then you come back and see there is no improved neighbor in the third neighborhood, and then only you will move to the fourth neighborhood. And suppose in the fourth neighborhood you found an improved solution, the search will go back and start from the first neighborhood. Is it clear? Why are we doing this? Because the size of the first neighborhood is smallest among all the neighborhoods. So we trying to reduce the computational effort. Is it clear? Just you can say clear. Question is there. Yes, it is clear. So this algorithm is written in such a way. If you now come back and read it, it is written in such a way. First, you initiate with an initial solution and you choose the neighborhoods you are going to use. You set I is equals to 1, and suppose there are this k number of neighborhoods. So you start a for loop. I am not starting a for loop, I am starting a while loop. It is just checking if I is less than equals to k. Find local optima S dash with respect to the ith neighborhood. So suppose I is 1. And then you check if a solution is local optima in that neighborhood or not. If it is so, move to that solution and update I to 1, move to the first neighborhood. If it is not the case, then increase I to 1, increase I by 1, and then again search in that neighborhood. So it is just doing what I explained earlier. It always move to the next neighborhood if no improvement is found in the previous neighborhood. And if you find an improvement in one neighborhood, you just circle back to the first neighborhood. We are circling back to the first neighborhood. Is it clear? Why multiple neighborhoods? Local optima depends upon the neighborhood. A solution may be a local optima in neighborhood 1, but not local optima in neighborhood 2 and 3, or so on and so forth. Benefit of neighborhood VND. Search breaks out of local optima deterministically. You don't require stochasticity in this algorithm. You may require it, but you are not employing it over here. Explore search space more thoroughly because you are searching larger and larger neighborhood. Naturally balances intensification and diversification. So every time you move to a different neighborhood, you are diversifying. Every time you are coming back to the first neighborhood, you are intensifying. Small neighborhood, fine grained search; large neighborhood, broader exploration area. Okay. often performs standard, it often outperforms the standard local search while staying simple. Obviously, we are searching larger and larger neighborhood, it should perform better than local search. If your neighborhood structure is such that it is not benefiting, that it may not perform better than local search. Examples of variable neighborhood descent I just talked about: swaps, insertion. By the way, this should be over here because insertion is smaller than swap, huh? So insertion should be above. Insertion size of the neighborhood of insertion is smaller than swap. So it should be like that. But yeah, you get the idea. The strategy use, yeah, so we have talked about this. So you always start from the first neighborhood. If you find an improvement, if you don't find any improvement, move to the next neighborhood. Now, difference between variable neighborhood descent and variable neighborhood search. Variable neighborhood descent is deterministic. Variable neighborhood search is randomized. So what it is doing is, variable neighborhood search, once it is in a neighborhood, it is stochastically searching that neighborhood. It is randomly generating neighbors and searching that neighborhood. In VND, it is deterministically searching the neighborhoods. That is the basic difference between variable neighborhood descent and variable neighborhood search. One is deterministic and the other is stochastic. I'm not talking about variable neighborhood search anymore, but that is the idea. Okay. By the way, this is not very appropriate because variable neighborhood descent is also doing diversification, but I have written it like this because it is stochastic, and that's why it is written like this. Okay, so this is the reference book I'm using. And before I close, I can give you an open stage because I have 10 more minutes. I would request you to uh, come to LinkedIn and send me a connection request if you want, obviously. And all the resources will be available at this link. I haven't yet obtained the recordings. Once I obtain the recording, it will also be available over here. So if somebody is here, you can just kindly unmute every participant. Explain this again. I'll explain this again. Can you? Yeah, I will explain the process again. Just a minute. If somebody is here from, if the host is here, kindly can you unmute everyone for 10 minutes? Or you can just allow everyone to unmute themselves. I don't know. Yeah, I will just explain the variable neighborhood descent again. So what we are doing is, first of all, we have to define different kinds of neighborhoods. So suppose this is shift neighborhood, this is swap neighborhood, and this is two opt neighborhood. Suppose for the time being. And you are starting with the variable neighborhood descent. So I start with an initial solution S. I search the first neighborhood N1. If I have found an improved solution, the search will restart with the first neighborhood N1. If I have not found an improved neighbor in neighborhood N1, the search will move to neighborhood N2. If there is an improved neighbor, I will move to that improved neighbor and the search comes back to the neighborhood N1. If there is no improved neighbor, the search move to neighborhood N3. Again, if there is no improved neighbor in N3, the search will move to N4. Otherwise, if there is an improved neighbor, we will move to that improved neighbor and the search comes back to neighborhood N1. Is it clear? Whoever was asking? I don't see the name, by the way, so that's why I'm saying, did you understand? Hello. Okay, so I hope it is clear. I don't see an answer. Any more questions? I'm sorry, I'm not able to make you let you unmute yourself, but yeah, you can write your doubts in the chat. Yeah, so process moves back to the first neighborhood on find. Yes, yes. The search process moves back to the first neighborhood. That is. what it is doing. That is because my first neighborhood is the smallest neighborhood. The size of that neighborhood is small, and we are trying to reduce the computational effort. Both in neighborhood descent and neighborhood search, variable neighborhood descent and variable neighborhood search, this happens. The search always moves back to the first neighborhood. Okay. All right. All right. So I'll just discuss the plan for tomorrow then. In the meantime, if you have something to say, you can write it. So the plan is we will talk about the basics of population-based metaheuristics tomorrow, and then we'll cover genetic algorithm. And likewise, if I'm seeing that we have time, I think we'll be able to cover ant colony optimization as well. Okay. There will be some new concepts because the concepts we have used here, like the representation and neighborhood generation, also will be utilized in another way in this population-based metaheuristic. But yeah, we will take some ideas, and there are some things to discuss before going into the algorithm of genetic algorithm and colony optimization. So that is the plan for tomorrow. Okay. If there is no more doubt, then yeah, you can leave. Thank you. And do connect me with LinkedIn if you want. Okay. Thank you for joining. I will leave the meeting as well. Yeah, there's one question, I guess. Okay. No more questions. All right. So I'll leave the meeting. You all can also leave the meeting. Thank you for joining. You all can leave the meeting. Huh? So I see some people are still here. You can just leave the meeting.